The rule for finding the derivative of a natural log function is as follows. The derivative with respect to x of the natural log of any function here is always equal to, and we're going to call it a u, whatever's there, because it won't always be just a plain x. So we're going to call that clump of stuff there a u. So the derivative of a natural log of u is always u prime divided by u. So in other words, you take the derivative of what's after the log and stack it over what's after the log. And that's always, it does not involve the power rule. Okay, that's a rule for finding the derivative of natural logs. U prime over u. So for example, we have y equals the natural log of x. So that means that the first derivative is equal to, what's the derivative of x? 1 over x. No power rule. So the derivative of the natural log of x is 1 over x. So when you take the derivative of a natural log function, the natural log does disappear. Pretty easy. Let's look at another one. Let's take f of x equals the natural log of 3x. So the derivative would equal the derivative of what's after the log, which would be, what's the derivative of 3x? 3 over 3x, which will simplify to 1 over x. So interestingly enough, the natural log of 3x has exactly the same derivative as the natural log of 1x. Here's why. If I take the original function and I split it using the properties, that would be the natural log of 3 plus the natural log of x. Right, guys?
Right.
Okay. And the derivative of a constant is just 0, and the derivative of this is 1 over x. So that is why they end up having the same derivative. Let's take a look at this one. Y equals the natural log of x cubed plus 2x plus 1. So if we want to take the derivative, we simply take the derivative of what follows the logarithm. So that would be what? 3x squared plus 2. And stack it over what's after the log. It's pretty easy. Most people don't mind these at all. For this example, we have g of x equals what? X ln of x. What is the x doing to the ln of x?
Is it multiplying? In front of it?
It's multiplying, right?
Yes.
So in calculus, how do we take the derivative of two things that are multiplied together? We use the product rule. We have a product rule for derivatives. We don't for integrals, but we do for derivatives. So if you have two variable functions, and we have x and natural log of x, multiplied together, if we want to find the derivative, we have to apply the product rule. So g prime of x equals, I'll do this over here, the first is x, the second is ln of x, and then we have d first is 1, and d second would be what? 1 over x. So the product rule states we take first and multiply it by the derivative of the second. So x times 1 over x plus second times derivative of the first, which is 1 times natural log of x. And we clean that up and we just get 1 plus the natural log of x. So when you take the natural log of just a simple function, of a just a simple natural log, the natural log does disappear. But if you're doing the product rule or the quotient rule or the chain rule, a lot of times it doesn't. So just be very careful. Any questions about this one? No?
So you just leave the natural log for these times?
Well, because it ends up, the original function is part of the product rule. It's why it's still there. So don't assume that the natural log will always disappear. Okay, for the next two examples, they look very similar, but they are worked very differently. The first one, we have y equals the ln of x, and the whole thing is to the 4th power. So basically, it's ln of x times ln of x times ln of x times ln of x, right?
Yep.
That's a parentheses to a power. This is a chain rule problem. Anytime you have parentheses to a power, it is a chain rule. This guy isn't. Only the x is to the fourth. So that's just a basic natural log problem. So let's talk about the chain rule problem first. To take the derivative of anything, regardless of what it is, to a power, you simply do power times coefficient. So 4 times 1, down 1 on the power, times the derivative of the inside. And what is the derivative of the inside? 1 over x. So that just gives us 4 natural log of x quantity cubed all over x. So because it was a chain rule, the natural log didn't disappear. It remained there, but to 1 power less than it started. To take the derivative of y equals natural log of x to the fourth, not the quantity, just the x to the fourth, we simply say, what's the derivative of x to the fourth? 4x cubed over x to the fourth, which reduces to 4 over x, right guys? Yeah. Another way to do that, if you wanted, you could rewrite this one as 4 natural log of x, and it would just be the coefficient times 1 over x. Either way, if you wanted to expand that and use the power property to turn it into a coefficient instead, you would still get the same answer. So for this example, we have y equals the square root of x plus 1. Notice there is no natural log. We simply rewrite it in exponential form and apply the chain rule. So y prime equals 1/2, down 1 on the power, times the derivative of the inside, which just becomes 1 over 2 square roots of x plus 1. So this guy did not have a natural log. Now I want you to do the same thing, but insert a natural log in front of it. So we're going to have y equals the natural log of the square root of x plus 1. Now, if you don't apply the power property first to this guy, and you try to just do the regular natural log formula, you have to do the derivative of this, which is this, right? All over this. And that becomes a complex fraction, but it really just would become 1 over 2 x plus 1. These two guys would end up coming together to make a whole. Do you guys see that? Mm-hmm. Okay. To me, that's a lot of work, and you're very likely to make a mistake. Mm-hmm. What you probably should train yourself to do is before you start, change it and expand it and look at it like this. It will make it so much easier for you to take the derivative. If you expand it first and look at it, you can see that the derivative is the coefficient, which is 1/2. And then to take the derivative of this, it's just the derivative of x plus 1, which is what? 1 over x plus 1. And so you would get the exact same thing, but with a whole lot less work. So I'm going to caution you, especially when you're working with square roots, make sure you expand them first and apply the power property and make it a coefficient rather than an exponent. It'll make it a whole lot easier for you to arrive at the correct simplified answer. So for this example, we have h of x equals the natural log of x times x squared plus 1 quantity squared, all over the square root of 2x cubed minus 1. To avoid having to do the product rule, the quotient rule, and the chain rule all together, we're going to split that into 3 separate logs. And the further you expand it, the easier it will be to take the derivative. So I'm going to let the first one be natural log of x, plus the second one will be the natural log of x squared plus 1 squared. But I'm going to go ahead and apply the power property and change it to 2 natural logs of x squared plus 1. And then this is in the denominator, so it will be minus, and it's a square root, so it will be 1/2 the natural log of 2x cubed minus 1. Does anybody have any questions about how we expanded that? Okay. Just just remember that the ones in the denominator will be subtracted. Then just go through and take the derivative of each piece separately, of each term. So you take the derivative of natural log of x, it's just the derivative of x over x. Bring your coefficient with you, and the derivative of this guy for the second term is 2x over x squared plus 1 minus 1/2. The derivative of this is 6x squared, and stack it over 2x cubed minus 1. And then we'll just go through and clean that up. We have 1 over x plus 4x over x squared plus 1 minus the 1/2 and the 6 reduced to what? These two reduced to 3x squared all over 2x cubed minus 1. And I'm supposed to make you get a common denominator because that's what the book does, but I don't really see the point. If we're not going to set it equal to 0 and solve it for something, there's no reason to get a common denominator. So I'll let you stop right there if you would like. So we have f of x equals the natural log of the absolute value of cosine of x. I'm not sure why they threw the absolute value on there, but it doesn't affect the answer. So we have f prime is equal to the derivative of, what's the derivative of cosine?
Negative sine.
Negative sine over cosine. And that equals negative what?
Tangent.
Tangent of x.
Sweet.
That's it. And that's pretty much wraps up differentiation of natural logs. And in a moment, we're going to look at a couple of applications to the derivative.